Hi, welcome back to my Tinyverse. Today we're talking about tiny features and the according tiny tools for them, especially a face trepanning tool. I have a bunch of parts out of one 4301 stainless steel that have a feature very similar to this pin with the groove around it. My first idea was to use a 1mm end mill and do it on the rotary table and just mill this ring-shaped groove. And I tried that and it's awful slow and rather hard to hit tolerances or close tolerances, and a good finish too. So what I decided to do, I made a face grooving tool or trepanning tool. People know these in a larger scale to cut out, for example, rings or discs out of sheet metal or do bulk material removal. John Saunders did a video with Mr. Diebold, and they did a video on trepanning to save material. I will put a link to the video down in the description. It's, the Diebold videos are very watchable and very educational. So what I did, I ground this tool, and then this has all the dimensions needed to create this exact feature. 3.8mm OD on this large diameter and 1.4mm for the pin. It's all baked into this tool. You just grab this in a collet, you plunge in, and you have your dimensions. You could do this with this tool in a boring head too, and then it would be adjustable. But there is a reason why I don't do that. The operation I'm doing requires two tool changes. And I'm changing from a relatively short collet with an end mill to do some milling on the part to a boring head, for example, with the trepanning tool. And there is a immense length difference between those tools. And there's a lot of Z-axis cranking or power feeding. And if I can, I don't do that. So I made this tool to be just as short as a small end mill, and this will solve this problem. So I ground already one. I will grind the second one just to have a spare one, and I will show you the process and also how I came up with the geometry of this tool. As you can see, it's relatively tiny. I ground it on the Deckel S1 tool cutter grinder. You could do this on a D-bit grinder too, or on a surface grinder with a spin fixture, or even on a milling machine with a indexing head, for example. There are many ways to grind tools. It doesn't have to be a 600 kilogram tool and cutter grinder. And the material I'm using is just a 4mm carbide end mill that's no longer useful. I make those myself. Here we are in CAD. You can see the tool in red, and here in gray, this is the part or a demo part with the feature in it. And to be honest, I modeled this only so you have something to look at. What I used is just this, a 2D sketch. So let's look into the sketch and see how I came up with the geometry for this tool. This inner circle here is diameter 1.4. That's our pin diameter that we want to create. And we have a diameter 3.8. It's this circle highlighted in blue. This is the OD of the pocket we're cutting. And then I just highlighted here in blue, draw in a shape for a tool that kind of fits in there. The cutting edge needs to be on center line, and then you add some clearance angles to the side so it doesn't hit the side wall back here. You need also some clearance to the pin just to make it cut free. In my case, I choose 5 degrees. That's arbitrary number. You could also go for 3 or 9 or 7 or something. And the 60 degree here, this is just a convenient number. 65 would be too much, and at 55, this would create an awful fragile tool. This is a very acute angle up here, And this is very fragile then. 60 was kind of a compromise. Otherwise, I would have to grind a double bevel. You could also do something like grind one bevel like this, then like this. That way, you end up with a less acute angle up here and with more stable tool. But I figured for this simple tool, this is good enough. What you also could do is you could put in a circle like this. And grind clearance like this. And then your tool geometry would look like something like this. You have a small bevel and then a radial clearance grind down here. But that requires to do an off-center grind, and that's a little bit more work. In all honesty, a little bit more work than I was willing to put into this tool. So I figured this will do fine. The 1.5 is important because if we leave it like at 2 millimeters, we get some weird geometry, but it also will hit the back side of the bore. So that's the reason for the 1.5. And you don't want to go lower than that. Well, you can, but that minimizes the cross section here that supports the cutting edge by a lot. So don't do that. Try to keep the tool as massive as possible within reason. So let's exit. Oh yeah, and for grinding, then I just printed out a screenshot of the sketch with some of the dimensions that I added, like the 1.2 here and the 0.7 millimeter up here. Oh, what I didn't model in this for this cutting tool is the front cutting angle clearance. As you can see, it's just a flat tool right now, and this way, this is the correct orientation now, it would not cut. You would need to add a 5 degree, something like 5 degree clearance grind to the front to make it cut, and I do that on the real tool, but I couldn't be bothered to model it. So let's go to the tool and cut a grinder where it makes some carbide dust. So over at the Deckel S1 tool and cutter grinder, since the machine is usually set up for something completely different, it's first a game of straightening out all the axes for the needed operations. In this case, the first thing we need to do is grind the prismatic shape of the cutter. You usually don't need to indicate the axis on a machine like this, since we're grinding fairly small features. Just aligning them with the relatively good graduated dials on all the joints is more than adequate. Clamping our blank, a 4mm end mill shank in a matching collet. And the first operation is to split the blank in half. This is basically the first step that we also would do on a D-bit. Touching off, and then it's just a matter of stepping in and grinding away the carbide. You might notice that I plunge into the material and then pull the grinding wheel out to the end of the blank. That way my outside corner of the wheel stays relatively sharp. So, sped up. I don't want to subject this wheel to very heavy cuts, that's why I'm going relatively slow. This is more of a precision wheel. And here you can see the motion that I'm doing from the outside. The right hand is advancing the work towards the grinding wheel, and my left hand is doing the back and forth movement of the table. And time to check our progress. I checked it before, this is the final inspection, just cut out the previous measurements. And the blank was 4mm in diameter, and the digital micrometer says 2.005 millimeters, so 5 micron on the cutting surface oversized. That's perfectly fine. Moving over 90 degrees, looking at the print, we're grinding this step here. This is to come from 4 millimeter diameter down to 3.8. Means 4 minus 3.8 equals 0.2, but we only need half of that because it's on both sides. We only have to grind 0.1 millimeter away. And I'm not grinding the relief angle yet. I'm just grinding all 90 degree surfaces. Bluing it up. This makes life for me while grinding easier. And then we hog away the 0.1 millimeters of material. This is done in 2 or 3 passes basically. Okay, here you can see a facet that we just ground. Going back, final pass. Checking the overall width. This should now be 4 minus 0.1 millimeters. 3.91, 13 microns oversized. This is fine because we still have to grind the clearance angle, and when we do that we will probably touch the cutting edge a little bit. Indexing over 180 degrees from the surface we just cut, and now we need to remove all of this material. This is 2.7 millimeters. This is the largest stock removal, I think, and we're just using the same technique as before. We move the grinding wheel in, we plunge into the carbide, and then we move out of the material. That way, as I said, the wheel stays way sharper than it would usually. If you go in from the outside, the wheel will break down on the outside edge. Here you can see what we ground so far. They split in half, and then our 2 surfaces to create the width of the tool. And there is also the chamfer on the top left from the original end mill shank that we use. Now we do the 60 degree cut. Now it's getting interesting. We set it to 120 degrees. That's because 180 minus 60 is 120. We blew it up completely, and now we grind in all the way until our ground surface meets the top surface, the halfway split of the carbide blank. Just when there is no blue line left, then we are where we want to be. And this is best done visually, just by looking what's going on, using a small magnifier like a 7x or a 10x eye loop. And you just go slow and move in. Oh, and carbide dust is, by the way, harmful. You should use, well, it's advisable at least, to use a dust mask and or dust extraction. As you can see, the blue line is now getting narrower and narrower. And taking some time to take a look at it, to good idea to rotate it a little bit so the light reflects a little bit different. This will give you a good idea of what's going on. Still a faint blue line left. And the closer and closer I get, I work a little bit slower and more careful and inspect what's going on a little bit more. Yep, still a line left. We're getting awfully close. Still a tiny, tiny line left. There we go. Now we have a sharp edge transition from the two surfaces to each other. Means we should be matching up our design drawing pretty well. I rotated the spindle 180 degrees or to 270 degrees, which is the opposite side, and used the finer just to move in another 5 degrees to grind the 85-degree clearance surface on the inside. And in a second you will notice something. When I turn on the grinding wheel, usually it's advised to grind carbide with the grinding wheel into the carbide, into the cutting edge. Here I'm grinding out of the cutting edge, and this is not ideal. This will create some minor chip out on the carbide just because of the brittle nature of carbide. It's just as it is. High-speed steel wouldn't do that. High-speed steel had other problems. Here we would get a fancy burr on our high-speed steel. For a very good result, I would have to run the wheel in reverse, which is totally possible on pretty much all tool and cutter grinders. But since it's not the main cutting edge, in the end I got away with it. And again, we're just grinding until the blue line completely disappears ever so slightly. There is still... And here we are grinding the back side of the tool to create the 1.5mm height of the geometry. As you can see here, it's now fully ground, and we still have this chamfer on top left from the original shank of the end mill. Means we have to reorient the tower on the carriage, opening the bolts and spinning it around 90 degrees. Setting our 5 degrees of clearance angle. and moving the indexing head of the grinder in way farther towards the grinding wheel so we can actually reach it. Moving the table stops just so we don't bump the grinding wheel into something. And also something I do on the tool and cutter grinder is I use a small rubber band on the stops to, in some cases, to keep the carriage moved to one side, to kind of act as a auto repeat or a auto reverse for the carriage. Sometimes very useful. And here we're just grinding the end to a 5-degree clearance angle. This is really not a lot of material to remove. This is going fairly quick here. So we're over at the milling machine. I have a piece of stainless clamped and the tool in a collet. So let's try a test cut with it. I'm going to run it at 2000 RPM and a power feed of 20 millimeters per minute. But first we will do a very mild touch off on the surface to get our C height. And as you can see, this is the motion that the tool will take once it spins. This power feed is 10 microns per revolution, and to my liking is almost too fast. Unfortunately, that's the slowest feed this machine allows. But as you saw, it does a really nice job of plunging into the material. Let's do another one, maybe by hand feeding. Let's step over a little bit and do another one. I think doing it by hand, feeding up the table, is a little bit nicer. Power feed on such a short distance, a little bit iffy. Okay, let's do a last one from a slightly different perspective. In the end, the hand feeding was way more sensitive than using the power feed. The table elevation on the Deckel FP1 with the hand wheel is very sensitive and very easy to manipulate. And that's also what I did on the final project when I did the actual parts. So I hope all of this kind of made sense to you. Thank you all for watching, and I'll be back.